Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Adaptive Integration. Adaptive integration is a technique used to compute integrals more efficiently by dynamically adjusting the method based on the function being integrated. Traditional integration methods like the trapezoidal or Simpson's rule often apply a fixed step size, but adaptive integration adjusts the step size during the process depending on the function's behavior, leading to more accurate results with fewer computations. Adaptive methods adapt to the complexity of the integrand, e.g., if the function is smooth and changes slowly, the method uses larger intervals and fewer sample points. If the function is highly variable, such as near a singularity or a steep peak, the method uses smaller intervals and more sample points to improve accuracy. Common adaptive integration methods are: adaptive trapezoidal rule. It is the simplest adaptive method based on the trapezoidal rule. It recursively subdivides intervals and uses trapezoidal approximations to estimate the integral, adjusting the step size dynamically. Adaptive Simpson's rule. This method uses Simpson's rule to estimate the integral, which is more accurate than the trapezoidal rule. Like the adaptive trapezoidal rule, it refines the interval size based on the complexity of the function. Romberg integration. This technique combines the trapezoidal rule with extrapolation to achieve higher-order accuracy. The method adapts the step size by combining results from multiple trapezoidal approximations at different levels of refinement. In this lecture, we will explain the implementation of Simpson's rule, which is the most commonly applied method to adaptive integration. Consider the integration of f(x) over the entire interval from a to b, using the two-panel Simpson's 1/3 rule. Where x0 is a point within the integration interval and SAB is the approximation to the integral of the curve shown in the figure, with the Simpson's 1/3 rule, which is expressed as follows. Evaluating the derivatives in the truncation error term is not an efficient way of estimating the error. We wish to have an error criterion that does not require evaluating the fourth derivative of f. Having the integral and approximating each half with Simpson's 1/3 rule, we obtain the difference between two-panel and four-panel Simpson's estimations is obtained as follows. Here, we assume the fourth derivatives are approximately equal. The error term is 15 times that of SAC plus SCB. By incorporating a user-supplied tolerance, a criterion for terminating the numerical integration can be expressed as follows. This observation provides a suitable stopping criterion that does not require the fourth derivative of f. Also, in general, the 1/15th factor is usually replaced with a more conservative 1/10th factor to compensate for the error in the above assumption. The advantages of the adaptive integration are: adaptive integration is suitable for recursive programming. Trapezoidal or Simpson's rules can be efficiently implemented into adaptive integration algorithms. Functions depicting sharp changes can be effectively integrated. The accuracy of the final estimate can be predetermined by imposing a tolerance value. The disadvantages of the adaptive integration are: it is applied to explicitly defined continuous functions. It is not suitable for highly oscillating integrands, improper integrals over infinite or semi-infinite intervals, or discrete functions. Note that the order of error for SAB and S2AB is h to the 4 and h over 2 to the 4, respectively, which makes SAB and S2AB suitable for Richardson extrapolation. Then, the accuracy of the numerical estimates can further be improved by the following extrapolation formula. Now let us use adaptive Simpson's rule to estimate the given integral within epsilon equals 10 to the minus 5. We begin by integrating over the range from 0 to 1, using a two-panel Simpson's rule. We require a point at x equals 1 over 2, which gives an estimated value of 0.69444444. Next, we divide the interval into two subregions. Applying Simpson's rule to the first subregion from 0 to 1/2, we obtain 0.4055, 55, 55, 56. Applying Simpson's rule to the integral over region from 1/2 to 1, we get 0.28, 76, 98, 41. Recall that we had already calculated S1. Adding the numerical estimates of the two subregions gives S2, which is found to be 0.69, 32, 53, 97. When the convergence test is checked, it is seen that convergence has not yet been achieved. Recall that we have already calculated the marked area, S1, on the left. To improve estimate, we will split this region into two subregions. Then, all we need to do is to apply Simpson's rule to the integrals. The S2 is obtained as follows. Upon checking the convergence criterion, we determine that the estimate for the integral over the first half has yet to converge. Also, notice that this subregion is half of the entire integration domain. Therefore, we also have the convergence tolerance. That means we will further subdivide this region. Note that we already know S1, so there is no need to calculate this. We split the subregion on the left into two smaller subregions. S2, as the sum of the estimates of the subregions, is found by applying Simpson's rule as follows. The subregion S2 is a quarter of the entire integration interval. At this stage, we observe that the convergence criterion for the integral over the first quartile is met. Note that the epsilon value was replaced by epsilon over 4 since the integration interval is the quarter of the entire interval. We have S1 2-panel and S2 4-panel estimates. We can apply Richardson's extrapolation to obtain a sixth-order accurate estimate as follows. Now, we move on to the next subregion from 1/4 to 1/2. The S1 estimate has already been calculated. We divide the S1 region into two subregions and apply Simpson's rule on both regions. We observe that the convergence test for S1 and S2 is satisfied. Now, we will apply Richardson's extrapolation to obtain a more accurate estimate, which is 0.1823, 2157. The integral from 1/2 to 1 was previously estimated as S1. To find a more accurate estimate, we divide this interval into two subintegrals. Applying Simpson's rule to these integrals, we obtain 0.28, 76, 83, 15. The convergence test using S1 and the more accurate S2 reveals that S2 is the converged result within the given tolerance value. Using the S1 and S2 estimates, the sixth-order accurate extrapolated value is found to be 0.28, 76, 82, 13. The numerical integral over the whole domain is the sum of the numerical estimates of the three subregions. Summing up the estimated values, We find the final estimate to be 0.693147 Since we know the true value of this integral, we can calculate the true error, which is found to be 6.544 times 10 to the minus 8. This is a much better result than the level of accuracy requested in the question. The reason for this is that the accuracy of the result is refined by incorporating the Richardson extrapolation method. With this note, we conclude this session. That is all for now. See you next time with another topic. Bye.